Hey there. Okay, so now we're going to talk about sequence stratigraphy in seismic data. Okay, so this is a really fundamental technique that we use to understand depositional systems and their evolution through time. And so sequence stratigraphy has been around for quite a while, and I'm going to talk about that first and then get into how it appears in the seismic data and how we can use it. So first, like I mentioned, we want to focus on sequence stratigraphy. There is so much information that I'm not able to cover in just 15 minutes or so. So I want to point you to the SEPM Strata website because they have so much more information. They have exercises, they have definitions. It's a really rich treasure trove of information. Okay, so just a brief history. So back in the late 1970s, Peter Vail, and some other workers who were at what was formerly Esso and is now ExxonMobil, kind of came across a technique to interpret seismic cross-sections in terms of their depositional sequences and environments. And so what they had at the basis of this were two key assumptions. First, the first thing they had to recognize was that seismic reflections define chronostratigraphic surfaces, things like bedding planes and unconformities. And then second, they proposed that the changes in the reflection geometry are primarily controlled by eustatic or global changes in sea level. And so with these reflections, and because of these reflections and how they came to understand them with the use of 2D seismic and well logs, they realized that the boundaries that they're seeing in seismic were reflection terminations. And so this is a framework that we use in sequence stratigraphy and also seismic stratigraphy today. And so this is an example, the original example from 1977. And you can see that they were working with quite a few well logs and some 2D seismic. And they had to spend a bit of time trying to understand what exactly the reflections were and how everything lined up. And so from this, the framework they created helped identify these co-eval deposits and predict reservoir distributions. So it's very well used in hydrocarbon exploration and development. And one of the things I always like to pause and mention, because Peter Vail went to the same university I did, obviously not at the same time, but I remember my professors told us about how he had told them that during his time at Exxon, like this took years to develop this sequence stratigraphy framework. And you know, they weren't producing, their company wasn't necessarily happy that they weren't figuring out this puzzle, figuring out exactly what was going on with the seismic data. And so they were really close to kind of getting in trouble professionally when they finally had their breakthrough. So while this seems like something that's pretty straightforward and easy to understand to us now, it was something that years of work went into. And, you know, as you go through your careers, wherever your career may be, you may have these problems that just, they don't come across answers very quickly, but it may take time, years of thinking and trying to understand and develop a new technique like they did. So as I mentioned, part of this is founded on the idea that the reflections we're seeing are chronostratigraphic, so they're age equivalent. The other way that this could be would be if they were lithostratigraphic, so they were rock types that we were seeing in seismic. And when you think about rock physics properties, you know, initially it would make sense that the reflections were more related to rock types than time and the age equivalence. So it's something to just pause and think about, you know, after this lecture to make sure you understand it. But what we're seeing in seismic is chronostratigraphic. It corresponds to these physical boundaries, these unconformities, and it's really essential for when we're doing seismic mapping. And so just to kind of show an example of this would be an example, and it's from the Hart textbook, of what we would see if it was a lithostratigraphic interpretation. So if it was lithostratigraphic, we would see in seismic, let me get my pointer on here, we would see in seismic reflections kind of at the base and the interface between these two groups. But you'll notice because this overlay is transparent that that's not what we're seeing. Okay, so when we have the chronostratigraphic boundaries that we're seeing, it looks more like this. So again, the same data where we have mapped out some of the main reflection patterns here. And so those are time equivalent surfaces. And, you know, knowing what we know now, it makes sense. We can see this building out into the basin. So we've got lots of different potential types of rocks and lithologies because we know geologically that we have a coastal plain followed by a shoreline down to the slope and then out of like the toe of the slope and then going distally. And those patterns that we're seeing in this lower image are not what we're actually seeing in the seismic. So hopefully chronostratigraphic, it's stuck in your head now. Here's another way to look at it because it's such an important concept. So if we were mapping and looking at, so here we've got our well logs and we've got two sequences that have happened. So we've got our very shaly, sandy, more shore face over here on the left, and then we're moving out into the basin, and it's a bit shalier off to the right of this figure. And so what we're seeing are the gamma ray change. And so while, you know, here we've got a sand on the left-hand side, there still is actually a change in the rock properties during this unconformity of progradation and then retrogradation back and forth and back and forth. And so that is what ends up resulting in the acoustic impedance difference, even when we've got sand or shale, because there's a lot of time that is passing where that's allowing compaction, dewatering, you know, all of that stuff that goes on to change the acoustic impedance properties. Okay, so I'm going to go through a quick review of some stratigraphic kind of key terms, talking about how we may mark the seismic. And so I've got some lovely slides from Art Saylor, who has taught some kind of carbonate workshops for us. So here's, let's say, our seismic. Okay, so it's been interpreted. And so one of the first things we want to look for is top lap. And so this is where we are at the top of the cliniforms, and we'll mark some of these top lap features. We can see that they kind of terminate against that upper region. They truncate against it is the right word. And so we use these to help us define our sequence boundaries. And then next we have our downlapping surfaces. And so these are more basinward dipping strata, and they are more at the base of the cliniforms. So just going through these, we'll pick a few of them out. And then from those, we can pick our sequence boundaries. So they're kind of happening between the onlapping or the top lapping and the downlapping. We often also see onlap. And so here's some cases down further on the right-hand side. You can see the pink arrows. And so this is where you have some horizontal, subhorizontal strata that are truncating against a basinward dipping surface. So this is commonly formed. We often see them when the sea level is starting to rise and build back up. And so these can be other things that can help you define sequence boundaries. And then we often get erosional truncation, so now marked with the blue arrows. These are something that we may call an angular unconformity in seismic, and I'll talk about that soon. And so as we mark all those very quickly, these are other features that we may mark in our seismic to coincide with onlapping surfaces. And you can mark them by hand, you can mark them in PowerPoint, do geopoint as we call it. And so now we've kind of been able to pick out some of our sequence boundaries, marked here with SB and in blue, and then our maximum flooding surfaces marked in brown. We've got our high stands, our transgressive systems, and our low stands. And so just a few more definitions with our sequence boundaries. Those are boundaries where major depositional surfaces characterized by subaerial exposure, the erosional truncations, and then the basinward shift in facies. so building out into the facies. We also have our maximum flooding surface, which is the maximum landward transgression of depositional facies. And I always feel like this lecture is a whole bunch of words and definitions. And then we have our transgressive surfaces. And with those transgressive surfaces, there are, those are kind of like the first significant marine flooding surface over the shelf, with a sequence that's commonly very abrupt, and then deepening on the shelf, in the shelf in deep water. And so looking between those surfaces now, we can pick out our high stand systems track. So the progradation where the sea level is high. And then we've got our transgressive systems tract kind of marked in green. And so this tends to be a time of very rapid sea level rise, and then kind of like a backward stepping towards the, or landward retreating of depositional facies. And then our low sand systems tract. And that's where you have deposition when the sea level is low. And it's commonly being deposited kind of more off the shelf. And you can see that over here, that we've kind of are depositing these sediments off the shelf. Okay, so when we're starting to look for these features in seismic, the first thing we often want to look for is unconformities. And we're going to look at some examples of that. But first, I just want to remind you of some of the terms that I keep throwing out again and again. So I often we talked about top lap, we talked about on lap. So that on lap is more horizontal, sub-horizontal. Here we've got some top lap, we've got the down lap down into the basin. We've got sequence boundaries. Here we've got some truncation. And this is a figure from the Exxon or Peter Vale's 1977 Vale and Mitchum. Their kind of main study, and it's very classic. And so I always tend to come back to that when I'm interpreting. All right, so here we are in the Taranaki Basin. This is an image one of my students grabbed for me from I was walking by his computer, and I was like, oh, send me some images of that. That'll be great for this class. And so we can see a lot of features here. He was, having taken my classes, he sent me a zoom in of the seabed so that we would understand the polarity of the data. So in this case, the seabed is red. Okay, that's positive. So we're working in normal polarity. We're moving into the seabed, into the rocks, represents an increase in acoustic impedance. Okay, especially since we can't see the seabed in this section where he cut it off. And so I want to just kind of pause here, and we could kind of look for some downlapping features, some onlapping features. In this area of the Taranaki Basin, they have these huge cliniforms. So you'll see that's 800 milliseconds or so. And you could see how they prograde out into the basin. We could see some cases up here of onlapping. It looks like we may have some truncation, erosional truncation happening over here. We can see the downlapping over in this area too. And there's a lot of other stuff going on. So to go through these a little bit slower and one by one, downlapping, we're looking for those kind of inclined reflections that terminate down dip onto or against an inclined or horizontal surface. They typically represent basinward progradation of that sedimentary unit. So let's go back here and let's pick some out. All right, so trying to find ones that definitely terminate like right around here. We've got that red one that terminates, another red one right above it that terminates. Here we've got a red and blue one that terminate here. So you can kind of look at those and pick out some of those downlapping features. If we were in class, I'd make people come up to the board and point them out. Harder to do on a recording. Okay, so we got downlapping sequences. So we talked about a sequence being a relatively conformable package of reflections. They're bound kind of above and below by erosional unconformities or those onlapping or downlapping surfaces. Okay, so just to clarify that. All right. So some of the interesting features we can see when we do sequence or seismic stratigraphy is we can understand the sediment supply in terms of the rate of relative sea level rise. And so this diagram tries to illustrate that relationship. And the balance of the two factors between sea level rise and sediment supplies often determines the type of stratal stacking patterns that we're going to observe in the seismic. And so you can notice here how different combinations result in different geometries. So in the case of transgression at the top, when the sea level rise outpaces the sediment supply, you've got progradation down here in the bottom where you have low sea level rise, but a lot of sediments. And so you've got that progradational building out into the basin. This is another way to look at it. Here we've got our stacking packages with some information from well logs. And so if we have well logs, you could see how those gamma ray patterns, I kind of mentioned this before in, I think, lecture 1.7 or 1.8, where you can look at the gamma ray or the spontaneous potential and those patterns in your well logs to get an idea about stacking or what's going on. Are you in a progradational setting like we have up here at the top, where you've got that, I don't know, not fining downwards. They didn't call this a bell-shaped curve. And so you could see these different, if you have that well in one location, you've got the thicker sands on top, they get thinner, they're fining downwards. Where in the retrogradational set, as they call it here, you've got more of the fining upwards. And I think they called that a bell-shaped curve in the reference I used in the previous lecture. And so this and many other examples of this are shown on the SEPM Strata website. So highly recommend that. Again, highly recommend it. This is another example of trying to think about what's happening through time. I, for some reason, always get very excited when I see cliniforms in seismic. I don't know why. They just appeal to me. Because it's very easy for me to think about what's going on with time. So I can picture all of these sediments being deposited and building out into the basin. And so this is just an example of breaking it down through time. All right, so here we're looking at back kind of at that Kokako data set, and we see some different stacking patterns. Okay, and so we're on the Taranaki Basin. We're to the west of the North Island of New Zealand, the southern portion of the North Island of New Zealand. And we can see that progradation, that building out into the basin. Okay, so hopefully you're able to image that in your head too. We can tell now that we probably had a very high sediment supply compared to a very low change in sea level. So we're able to build out here. All right, so I want to kind of just spend a couple of slides talking about the importance of frequency content. Again, this was one of those foundational concepts, one of the things we really want to understand in our seismic area, our seismic data. And so here's a good example of what a pinch out looks like in seismic. So down here on the bottom, we've got this pinching out. So kind of this onlapping up onto a surface. And it looks to us, because of the frequency content, that it just pinches out, it thins out. I drilled a couple of prospects in the Gulf of Mexico that were pinch outs onto a salt dome. But in this case, because of the frequency content, you could actually have a real lithologic model where those sands don't pinch out, but rather they go up and over that structure. Okay, and so that means if you're drilling it for hydrocarbons, those hydrocarbons can continue to move up into the system, but you can't tell that because of the frequency content. So just something to keep in mind, that you can't see those very, very thin beds. Here's another example of looking at different frequency spectrums to see different elements of the depositional sequence. And so this is some work that was done at the University of Oklahoma a little bit before I got here. And what they've done is we've got the full stack data, as well as they've kind kind of pulled out just the higher frequency data, the lower frequency data. And so they're kind of comparing those and looking at them for different elements. So here we've got very high frequency data in this bottom left-hand side. We've got some of the lower frequency data where we could see those larger packages. And over here, we've got some of the kind of middle frequencies of the seismic data, which really shows some of those different stacking patterns. So a little kind of tool you can use in your seismic interpretation. Here's a case by Henry Postmentier and some of his co-authors where we can look at what we are able to resolve or see with different frequencies. So we've got the full frequency up here in the upper left. And so we see these channels. I'll talk about channels in lectures soon. We can see these channels. We can see some bright spots. When we look at the medium frequencies, you know, we're able to still see those channels a little bit weaker. They're highlighting more the major depositional elements. In this case, with the low frequencies, we're seeing things that are probably related more to the larger scale regional trends, not so much the smaller scale local features. You can see those channels don't show up as well. And then here with the high frequencies, we're seeing a lot more detail about the stratigraphic features. So you should feel free to take your seismic data, apply filters, and pull out different frequencies in order to analyze the different elements of what, say, 15 hertz data, a peak frequency of 15 hertz data can tell you compared to a peak frequency of, say, 50 hertz. Here's another example, again, looking at the low, medium, and high from that same paper. So this is a great paper. If you're into and trying to learn more about seismic geomorphology, I really recommend it. And here we're able to see a channel system right here. The higher frequencies kind of reveal a lot more detailed stratal patterns. The middle frequencies show us a little bit more of the internal architectures about what's going on. And then high frequencies, mid frequencies, the low frequencies are highlighting kind of some of the larger scale features, the different boundaries of the depositional features. All right, and so we'll get to this more later, but if you take those high, medium, and low frequencies and you plot them in red for low, green for medium, blue for high, and then you combine them with a transparency, you're doing something called spectral decomposition, which is a really great tool to use in seismic interpretation, and we'll get into it more in a later lecture when we talk about attributes. But I just wanted to show this example because many of you have probably heard the words spectral decomposition. And so when you think about breaking down and interpreting on just the low frequencies or the high frequencies, you're kind of doing the same process that you would be doing with spectral decomposition, where you're trying to image them all together. In his paper, Postmentier 2022, they talk a little bit about grid picking. And so there's only a few papers I've seen that really dive into this. And so I wanted to mention it here. So in this image, we see different grid spacings that you can do for your interpretation. You can pick and look at every 2x2 lines or every 9x9. And so oftentimes you want to balance out some of the level of detail you need with the efficiency of picking. And so that's kind of a crucial detail we'll have to think about as an interpreter. And of course, it all relates back to, well, why am I doing this seismic interpretation? Like, what's my purpose? And so here we've got what it looks like if the interpreter picks every 2x2 on the upper left-hand side. And then if we just kind of go down to the lower right-hand side, we can see how some of these features are more smeared out if you're doing it every 9x9. And so again, keep in mind why you're picking the data, why you're interpreting the data. All right, and then next to last slide. One thing I always like to mention is we use this word facies a lot as seismic interpreters or as geologists. But what we're going to be getting into and what we're going to be talking about are seismic facies. So facies are just ways we can describe these different packages. So sometimes we talk about biofacies, and this is where we're talking about that sedimentary unit based on its fossil content. Lithofacies we're talking about it in terms of perhaps the mineralogy or the grain size. And so lithofacies is different than seismic facies. Seismic facies is what we're about to jump into, where we're talking about the characteristics of seismic reflectors. So these will be things like continuity, amplitude, frequency contact patterns. And so as we go through, we want to make sure that we use these kind of terminology correctly. And so that'll be a fun lecture next. Okay, so just some of the key concepts. You know, just to remember that sequence stratigraphy and seismic stratigraphy give you a great framework for interpreting your depositional system and understanding it better. There's a lot of key elements and a lot of terminology that I went through. So SEPM Strata website is a great resource. But we talked about sequence boundaries, system tracks, different stratal terminations that you may see. I also highlighted how frequency content is very important. Making sure you understand the limitations of your frequency in terms of the pinch out example I showed, but also thinking about interpreting just certain frequencies, just the low frequency or the high frequency, because that can help enhance our interpretation. And so there's always multiple techniques, and we'll be learning more and more of these in the next few lectures that can really help you create and perform more robust interpretations. So in any case, thanks so much for listening.